So, in the last lecture what we have done is we have initially talked about the application of Fourier transform for solving the partial differential equations. We have provided the criteria under which condition I should use Fourier transform, I should use Fourier cosine transform, or I should use the Fourier sine transform, and we solved one problem on that Fourier cosine using Fourier cosine transform. Let me just quickly go through that problem again, so that I can explain it to you. We want to find out the solution of the PDE using Fourier cosine transform. The equation is del u del t equals k del 2 u del x square, where x lies between 0 to infinity, and with u x 0 equals 0 and del u del x equals minus mu, which is a constant. Also u and del u del x approaches 0 as x approaches infinity. So, the conditions whatever is provided, and since x approaches 0 to infinity, therefore, we will use the Fourier cosine transform. So, what you are doing basically, whenever the problem is given, you use the apply Fourier cosine transform on both sides of the given equation. So, once I am applying the Fourier cosine transform on the both side of the given equation, root over 2 by pi will come 0 to infinity, del u del t cos of alpha x dx equals k into root over 2 by pi 0 to infinity del 2 u del x square cos of alpha x dx. Now, the left hand side is nothing but del u del t is there. So, ddt I can bring outside, because you are taking Fourier cosine transform with respect to x, and 0 to infinity. If you see, if del t, that is ddt, I am bringing outside the integration sign, then it will become ddt into root over 2 by pi ddt of root over 2 by pi 0 to infinity u cos of alpha x dx, and this integral 0 to infinity u cos of alpha x dx is nothing but cosine transform of u. For this reason, on the left hand side we have written ddt of u bar c, which is equals to, here I am breaking the integral using by parts, and after that using the condition that del u del x equals minus mu when x equals 0 and del u del x approaches 0 as x approaches infinity, using these two conditions I am obtaining this integral. So, that from here you can again break the integral, and ultimately I am obtaining an equation like this. So, you are obtaining the equation d u bar c by dt plus k alpha square u bar c equals root over 2 by pi k mu. So, please note that using the Fourier cosine transform, the given second order PDE is transformed into an first order ODE. So, this is the first step, where you are converting the second order PDE into the first order ODE using ordinary differential equation using the Fourier cosine transform, and the solution of this I can find out. Just we have written integrating factor. I am not going through this, because this is simple one, and already you have done all these things. So, ultimately you are obtaining u bar c equals a e power minus k alpha square t in plus root over 2 by pi mu by alpha square. So, this is your second step, u bar c you are obtaining. Now, you have to find out the value of the constant a. To find the value of the constant a, we know that at t equals 0, u equals 0. Therefore, if you take the Fourier cosine transform, then I can say that at t equals 0, u bar c will also be 0. And using this condition, I can obtain the value of a as minus root over 2 by pi mu by alpha square, where u bar c is, I am obtaining this. So, this is your second step, where you are finding the solution of the given ODE. Now, the third step is, once I obtained u bar c in terms of alpha and t, I can, using the inverse Fourier cosine transform, I can find out the value of u x t. U x t will be equals to, using inversion formula, root over 2 by pi 0 to infinity u bar c into cos of alpha x d alpha, and I have to evaluate the integral. I am just keeping it like this. So, the result becomes 2 mu by pi 0 to infinity cos of alpha x by alpha square into 1 minus e power minus k alpha square t into d alpha. Further I can evaluate it, I am leaving it for you because this integration is easy to solve and you can find out the ultimate value. So, we will leave this integral position itself from where you can find the complete solution of u x t. Now, so you see the earlier problem we have done it using the Fourier cosine transform. Now, next problem, the similar problem equation would be similar, but we want to solve it using Fourier sine transform. Del u del t equals del 2 u del x square x greater than 0 t greater than 0 u 0 t equals 0 when t greater than 0 and u x 0 equals 1 if x lies between 0 to 1. Otherwise, for x greater than equals 1, it is 1 and u and del u del x approaches 0 as x approaches infinity. Although, here both x and t are greater than 0, but from the condition, especially from the condition that del u del x approaches 0 as x approaches infinity, regarding t nothing has been told about del u del t. So, we have to use the Fourier sine transform with respect to the function x not t. So, please note this one that although both x and t their range varies from 0 to infinity, but actually what happens from the initial conditions we are finding that the del u del x approaches 0 as x approaches infinity is given. Therefore, it is desirable to use the Fourier sine transform with respect to x, not with respect to t, because if we try to solve it using with respect to t, we will not able to provide values of certain parameters. For this reason, we will use the Fourier cosine transform, Fourier sine transform with respect to the variable x. Let us see the solution process now. So, we are applying here, we apply Fourier sine transform, I am just writing it as f s t with respect to the variable x on the given equation, that is del u del t. On your equation is del u del t equals del 2 u del x square. This is the given equation. So, you take Fourier sine transform with respect to x on this particular variable, on this particular equation. So, that root over 2 by pi 0 to infinity will come del u del t into, since with respect to x therefore, sine. So, it will be sine alpha x into dx. This is equals on the right side it will be root over 2 by pi 0 to infinity del 2 u del x square into sine of alpha x into dx. Since we are differentiating with respect to x, we are taking the Fourier sine transform with respect to x. Therefore, on the left hand side del t can come outside, and once del t is coming outside, your integration is 0 to infinity u sin alpha x dx, and that is nothing but from definition u bar s. So, that this we can write down, this implies d dt of u bar s. This is equals to, now I have to integrate the right hand side integral using by parts. So, directly I am writing it. First part will be del u del x into sine of alpha x 0 to infinity minus alpha into 0 to infinity del u del x into cos of alpha x into dx. This you will get, and the value of this integral, this particular part if you note del u del x at the lower limit this parameter vanishes, del u del x sin alpha x vanishes, and if you should note one thing that from the given condition del u del x approaches 0 as x approaches infinity. So, therefore, whenever you are putting the limiting value for infinity, then also this term will vanish. So, overall this term will vanish for both 0 and infinity. So, first term will be vanishing over here. So, that you will obtain root over 2 by pi minus alpha into 0 to infinity cos of alpha x into del u del x dx. So, again use by parts over here, root over 2 by pi into minus alpha into this will be u cos of alpha x 0 to infinity minus alpha square will come 0 to infinity u into sine of alpha x dx. So, after integration by parts you will obtain this. Please note that u approaches 0 as x approaches infinity. U approaches 0 as x approaches infinity over here, and also the value is 0. Therefore, this part will be 0, and so this becomes minus alpha square into this is nothing but u bar root over 2 by pi 0 to infinity u sine of alpha x dx is nothing but u bar s. So, this you are obtaining this. So, therefore, what you are obtaining, your partial differential equation, this one is converted into an ordinary differential equation, which is d u bar dt plus alpha square u bar s equals 0. So, I am writing the ordinary differential equation now, d u bar s dt plus alpha square u bar s, this is equals to 0. And the solution of this one directly you can write down u bar s equals a into e power minus alpha square t. So, where a is the constant of integration, the constant parameter. So, now I have to find out the value of a. What I have to do at t equals 0, let us see what happens. What is the value of this u bar alpha 0? Because u bar s alpha t is given as this one. So, what is the value of u bar s alpha 0? So, if I put the condition from the definition, root over 2 by pi 0 to infinity u x 0 into sine of alpha x into u x 0 into sine of alpha x dx. Now, if you see u x 0 has been defined already in the question, u x 0 is 1 whenever x lies between 0 to 1, and for x greater than equals 1 it is 0, it is given. Therefore, this integral actually I can break it into two parts, root over 2 by pi 0 to infinity 0 to 1 u x 0 is 1. So, you will obtain sine alpha x into dx plus root over 2 by pi 0 to infinity 0 into u x 0 is 0. So, it will be 0 into sine alpha x dx. So, this second term vanishes over here. So, the integration of this is root over 2 by pi into minus cos of alpha x by alpha, where it lies between 0 to 1. And if I put the value, I will obtain root over 2 by pi 1 minus cos of cos alpha 1 minus cos alpha divided by alpha. So, at t equals 0, I am obtaining u bar s equals this. So, if I substitute it in this given equation now, on this equation if I substitute this condition, then I can find out the value of a. Please note that t is 0 means this term will vanish, e power minus alpha square t will be 1 whenever it is t at t equals 0. So, that I can write down my a as root over 2 by pi into 1 minus cos of alpha divided by alpha. So, once I obtain the value of a, so I can rewrite now my u bar is as root over 2 by pi into 1 minus cos alpha by alpha into e power minus alpha square t. So, this is my second part is over. Once I have obtained u bar s in terms of alpha and t, now I can write down u x t using the inverse sine transform. So, that it will be root over 2 by pi is already there, 2 by pi will be now coming 0 to infinity 1 minus cos alpha by alpha into e power minus alpha square t into sine of alpha x d alpha, and you can evaluate this integral and you can obtain the result. So, we are leaving, as I have told you earlier, we are leaving this in this integration part, which you can do it of your own. So, the third part becomes u x t equals this particular integral. So, let us see, the problem was this one. So, I am taking Fourier sine transform on both sides of the given equation. I am writing this. From here, the left hand side is nothing but d dt of u bar s, and the right hand side I have to evaluate. So, I am evaluating, there I am using one condition, del u del x approaches 0 as x approaches infinity. So, that the first term, whenever you will put the limit 0 and infinity, the first term will vanish, you will have only the second term, that is the integral. Again use by parts and integrate it. Here again the first term will vanish using the condition u approaches 0 as x approaches infinity, and they are alpha square. So, you will obtain minus alpha square, and this integral is nothing but u bar. So, that you are obtaining the ordinary differential equation as this, whose solution is simple, a e power minus alpha square t. To find the value of a, I am finding at t equals 0 what is the value of u bar s alpha 0. Please note that this particular condition is not provided in the question. In the solution, we are just finding the value of this u bar alpha 0 by evaluating the integral using the definition of Fourier sine transform. And the function u x 0, we know what is the value. This is 1 whenever it is 0 to 1 and 1 to infinity it is 0. So, that second integral vanishes, and after evaluation we are getting u bar s alpha 0 as this function of alpha. Therefore, I can write down a equals this, and from here u bar s I am obtaining as a function of alpha t, and if I evaluate now, I will obtain the u x t, that is u x t equals this quantity 2 by pi 0 to infinity 1 minus cos alpha by alpha into e power minus alpha square t into sin alpha x d alpha. And if I evaluate the integral, I can tell about the what is the value of u x t. I am leaving it for you, which you can evaluate of your own. Now, let us see the another problem. Del u del t equals 2 del 2 u del x square. Similar problem, just we are giving some problem so that you can better understand how to find out the solution. Here it is x greater than 0 and t greater than 0 with u 0 t equals 0, and when t greater than 0, u x 0 is provided as e power minus x, and u and del u del x approaches 0 as x approaches infinity. So, as you have seen in the previous problem, whenever we are considering the Fourier sine transform, then one term will be coming del u del x, and the value of del u del x should be known as x approaches infinity, otherwise I cannot evaluate it. Therefore, for this problem also, to find the solution, I have to use the Fourier sine transform with respect to the function with respect to x only. So, what we are doing, your equation is given as del u del t, this is a special case, 2 into del 2 u del x square. Now, you apply Fourier sine transform with respect to x. So, once I am applying Fourier sine transform with respect to x, then you will obtain root over 2 by pi left hand side is same 0 to infinity del u del t into sine of alpha x dx. This is equals 2 into root over 2 by pi 0 to infinity del 2 u del x square into sine alpha x dx. So, the left hand side again will be d dt of u bar s, and the right hand side, if I evaluate the integral by parts, I will obtain the first one del u del x into sine of alpha x 0 to infinity minus alpha into 0 to infinity del u del x into cos of alpha x dx. So, once I am obtaining this equals again the first part will vanish as del u del x approaches 0 as x approaches infinity. The first term will vanish. For the second term, you will have 2 into root over 2 by pi, 2 into root over 2 by pi into minus alpha into 0 to infinity del u del x into cos of alpha x dx. So, if I evaluate this thing, then using the similar process, I can obtain the result as 2 alpha square u bar s. Please note that u 0 t has been provided as u 0 t equals 0 and u approaches 0 as x approaches infinity. I am using this condition in evaluating this integral. U 0 t is 0 and u approaches 0 as x approaches infinity. Using this, I can obtain the value of this integral as minus twice alpha square u bar s. Same thing I explained in the earlier example. So, directly I have written the result. So, that now your ordinary differential equation becomes this thing d u bar s dt plus twice alpha square u bar s, this is equals to 0, and the solution of this is not twice, but some constant a into e power minus 2 alpha square t. So, the solution is u bar s equals a into e power minus 2 alpha square t. Now, I have to find out the value of this a the same way, that is at t equals 0. At t equals 0, what is the value of u bar alpha 0, u s bar alpha 0. So, this is equals root over 2 by pi 0 to infinity u x 0 sine of alpha x into dx, and this value is given as u x 0 is given as e power minus x into sine alpha x dx. And if I evaluate this integral e power minus x sine alpha x, this is again a standard one, you can check it. I am writing the result directly, 1 plus alpha square into minus sine of alpha x minus alpha cos of alpha x, ranges from 0 to infinity. The value of x lies from 0 to infinity. If I evaluate this integral, I will obtain alpha plus 1 by alpha square into root over 2 by pi. So, once I am obtaining this, therefore, you can write down your a as this one, root over 2 by pi alpha by alpha square plus 1. And if I substitute it in the given equation, my u bar s now becomes root over 2 by pi alpha by 1 plus alpha square into e power minus twice alpha square t. And once I have obtained u bar s in terms of alpha and t, we can find out what is our u x t. U x t will be 2 by pi 0 to infinity alpha sine of alpha x by 1 plus alpha square into e power minus twice alpha square t into d alpha, and you can evaluate this integral of your own whenever we use this thing. So, just let us check it quickly. So, the problem was this, I am using Fourier sine transform on both sides with respect to x. Once I am using the Fourier sine transform with respect to x, I will obtain this value. So, d dt of u bar s is equals to 2 into root over 2 by pi into sin alpha x 0 to infinity minus alpha 0 to infinity del u del x into cos of alpha x dx, and using the condition del u del x approaches 0 as x approaches infinity, if I the first term, that is this limiting term, will be vanishing, where you are putting the limits of x as from 0 to infinity. So, only the second integral will be there. So, I have written this integral, and again if you evaluate it, then this I will integration by parts, I will obtain this one, and again the limiting value of the first term will be vanishing, as we know u 0 t equals 0. So, that at x equals 0 it becomes 0, and u approaches 0 as x approaches infinity. Therefore, first term vanishes, and for the second term the integral is nothing but the u bar s. So, that it becomes minus twice alpha square into u bar s. So, that your differential equation now becomes d u bar s dt plus twice alpha square u bar s equals 0, and its solution is nothing but u bar s equals a e power minus twice alpha square t. So, you are converting the PDE into ODE using the Fourier sine transform. Now, you have to find out the value of the constant a. To find out the value of the constant a at t equals 0, what is the value of u bar s alpha 0, that we are finding out. From the definition, you can write down u bar s alpha 0 equals this integral 0 to infinity u x 0 sin alpha x dx, and in the problem it is provided that u x 0 is e power minus x. So, I am replacing e power minus x, then just integrate it, because e power minus a x sin b x format. So, direct results I can put, and once I am putting the limiting values of x from 0 to infinity, ultimately I will obtain root over 2 by pi into alpha by 1 plus alpha square. So, once I am obtaining this, if I put in the last equation, I can obtain the value of a as root over 2 by pi alpha by 1 plus alpha square. So, that u bar s you can write down, so that using inversion u x t will be equals to 2 by pi, because root over 2 by pi is coming twice. So, it will be 2 by pi 0 to infinity alpha by 1 plus alpha square e power minus twice alpha square t into sine of alpha x d alpha.